and for having me. So I'll briefly tell something about the work that I've been doing for my PhD on the modeling of permafrost freeze-thaw processes, and thereafter also introduce the FARMWISE project. So yeah, it's the content for next 20 or so minutes. So my PhD project is on permafrost freeze-thaw processes. So here you can see an example from the biggest permafrost craters in Siberia, and here permafrost has quite a high ice content, and well, when it starts to thaw at a certain point, it tends to collapse actually in the landscape, and thereby really altering the hydrological functioning of the system here, and also releasing enormous amounts of greenhouse gases. And one of the key constituents here is then, of course, the organic matter that's in the permafrost and in the soil. And under the warming climate, the permafrost is changing and thawing. And as part of my PhD research, we actually set out to investigate seasonal freezing and thawing. And the final goal was if we could combine freeze-thaw models also with transport of dissolved organic carbon in the groundwater. So you have with these permafrost processes, you have more deep groundwater flows that might start to occur, transporting deeper dissolved organic carbon to the surface, and thereby potentially accelerating greenhouse gas emissions. Well, just a quick heads up, we didn't get that far into my PhD project that we actually included the modeling itself, but we do have some really nice results. So here we have like a typical snapshot of just a number of processes that could emerge under a warming climate. And these happen at the surface, but also in the subsurface. And that's actually what we're focusing on this interaction between the surface and the subsurface. So then in this research, we mainly focus on the transition between freezing and thawing. And this is the most dynamic part of permafrost, and this takes place in the active layer. And here, mostly temperature observations are then used to track the temporal evolution of the active layer. So this is just a quick snapshot how the active layer usually evolves over time. So the active layer usually about 1/2 to 2 meters thick, depending on where you are, and it seasonally freezes and thaws. And here the blue line is your lowest minimum temperature, and the red line is your summer temperature. And well, over the last 50 years, we can see that there's this gradual increase in air temperature. And if you project it even further on, you can see that over the next 10 years, the active layer deepens until you actually reach the base of your permafrost, and then your entire permafrost will be gone. So in order to study this active layer deepening, you can use heat transfer models to actually simulate how temperature propagates through the permafrost. So we have these heat transfer models, but we actually then need to accurately parameterize these models before we can start our simulation. And often temperature observations are collected, but you need actually information on the thermal properties in order to parameterize your numerical model. But those are way more difficult to collect in the field. So therefore, we actually set out if we could use temperature observations to delineate the properties. So instead of using a model and then using fixed thermal properties, we used the observations, the temperature observations, to then parameterize our model. So we had some data collected at the Tibetan Plateau, there in the red circle, which is characterized as quite unstable or transitional permafrost. These are some pictures from the area, and we had that data set, and we used the data set from that area as a case study site to see if our hypothesis would work. So the goal is that we have these temperature observations collected at different depths within the permafrost, as you can see on the right. And we actually want to use the temperature observations to determine the thermal properties. And for that, we use a heat transfer model. So it is using the soil thermal conductivity is in balance with your soil heat capacity, and you have to simulate the freezing and thawing. So for that, you use the latent heat of fusion. And porosity is an important variable in your really basic heat transfer model. So this is a conduction-only model, I should point out. And there at the left, you can see those are the temperature observations that are collected not as an air temperature, but just below the soil surface. So we don't model actually the surface energy balance. We solely look at the energy balance in the soil itself. So then our approach is we have our observations. We create a 1D model, which is about 30 meters deep. And at the top, our boundary is then the measured soil temperature at about 5 centimeters depth. And we have a specific temperature at the bottom. But then we need to, we want to determine these properties, so the thermal conductivity, the heat capacity, and the porosity. So actually what we did was we defined a parameter space for each of these parameters, which resulted in, 18 different variables for thermal conductivity, 16 for heat capacity, and 6, I believe, for porosity. And when you combine all the different combinations, you get 1,700 tornado models. And we simulated all of those models in a large batch simulation. So we have many heat simulation runs. And then we wanted to find out which of those parameter combinations actually best fitted our observed data, our measured data at all the different depths. And for that, we actually used 3 different approaches. So we have our 1,700 models, and then we use the root mean square error to see which model best fitted the data. We use the Klein-Gupta efficiency to see which model best fitted the data, and we used a Russell's error. And all 3 of these error measures actually focus on specific mismatches in between data and observation. So the root mean square error, for example, just looks at the difference between the two and minimizes the difference between your observed and your measured. Whereas the Russell's error, for example, focuses way more on a difference in timing of your signal, because that is more used for harmonic analysis. So you actually look at different aspects of your data. And that in the end proved also quite interesting, because you get different results. So here on the left, you can see a snapshot of the measured data from the permafrost. And here on the right, you can see that we just plotted the data that we measured at 80 centimeters depth, alongside with 3 of the best model results. So the Russell's, the root mean square error, and the Klein-Gupta efficiency. And depending on which error measure you use, you actually get a different optimal parameter space that best simulates your data. So even though you think you are objectively trying to fit your data with your model, depending on which error measure you use, you actually get a different result. So it's not really that objective, actually, because you as a researcher have quite some influence on that. So here on the left, you can see the parameter space that we investigated. So you can see thermal conductivity, heat capacity, and porosity. And this is just for the root mean square error. And then here on the right, you can see the optimal values are indicated with the black dots. So on the top row is the root mean square error, the second one Klein-Gupta, and then the bottom one the Russell's error. And you can see that actually the optimal values differ for each error measure that you use. So then our next reasoning was, so okay, we get different optimal values to simulate the same thing. What happens if we would then simulate a hypothetical scenario of temperature increase over permafrost using these three different parameter spaces, and just look at how the active layer of a permafrost area might develop over time. And here in figure B, you can actually see the depth of the active layer changing over time. And there's actually quite a significant difference between our different optimal model results that you use. So you get a difference in timing and a difference in magnitude between your results. So actually, there is a sensitivity in your thermal parameters that you use, but there's perhaps even a larger sensitivity in your error measure that you use to fit your data. So that was the first part of my research. And then thereafter came the next question. So we know that we can use this 1D model to simulate temperature fluctuations in the field, but what is actually the relation between sort of grain size and organic matter and these thermal properties? Because we know that, for example, the organic matter content has an effect on the thermal conductivity. It acts as a sort of an insulator. But can we actually also apply the same technique to these to see if we can determine the thermal properties, or actually determine the relation between organic grain size, organic matter, and thermal properties? So what we then set out was 9 column experiments. So we had these quite large columns filled with 9 different combinations of grain size and organic matter content, and we subsequently froze them, and then we thawed them again, and we measured temperature at the different depths within the column. And thereafter, we used the same 1D model to also simulate the same temperature propagation, and then we try to delineate the thermal properties again. So here we see some of these temperatures collected within the column. So you can see that as you start freezing, the temperature in your column, in your sample, goes to 0 degrees quite quickly. Then thereafter, we have your phase change. So pore water starts freezing really slowly. And then as soon as pore water is frozen, your temperature drops quite rapidly. So we fitted the same numerical 1D model to our observations. And well, you can see that depending on, so we have on the horizontal different grain sizes. So quite a small grain size to quite a large grain size at the bottom. And well, we could sort of fit the data to our models using again the Russell's error, Kling-Gupta efficiency, and root mean square error. But then if you plot your thermal conductivity against your measured organic matter content and against your heat capacity, you can see that only for porosity there is a clear sort of linear relationship between organic matter content and observed porosity. But for the thermal conductivity capacity, it proved actually quite difficult to use a numerical model to really determine the relevance, the influence of organic matter on thermal conductivity and heat capacity. But that's also because well, heat capacity is actually a really quite an insensitive parameter to estimate. So therefore, the range is actually quite narrow. So then the final part of research that we did was using another technique instead of temperature, or alongside with temperature, to detect actually the freeze-thaw front in permafrost, because and therefore we wanted to use ERT, so electrical resistivity tomography, and it is because if you collect an ERT sample over a permafrost area, the bulk resistivity has quite a strong is quite strongly influenced by temperature. So when temperatures are above zero, all the pore water is liquid. So you have a really low impact of temperature and resistivity. But as soon as your pore water starts freezing, you get a jump in your bulk resistivity, because the ice is a poor conductor of electricity. So we set out with a similar column experiment, but this time equipped with electrodes, to see if we could actually detect this freeze-thaw front using electrical resistivity rather than temperature. So just a quick picture of how the setup looked like. So we had 96 electrodes in rings spaced out around the column, and we have had 8 layers to detect the temporal evolution of this freeze-thaw front. So with these ERT observations, you will also always have to account for your sensitivity in your electrical resistivity, but also for your resistivity errors, because as you start freezing your soil matrix, the resistivity that you measure go up, but therefore also your error goes up. So in this figure, you can actually see that during the thawing phase, when the resistivity goes down, your error is a bit lower, and then during your freezing phase, your resistivity values are a lot higher, but your error is also a bit higher. So you have to account for that. So what we can see here is actually on the left are temperature observations. So this is when we froze our column, and this is where we thawed our column. And these are all the ERT inversion results from the thawing period. So here, figure 9, that is actually when the column was fully frozen, and you can see that there was a really high resistivity distribution throughout the column. But at number 10, you can see that the temperatures went up to 0 degrees in the entire column, so the temperature was increased. And here at the bottom, you can see this blue zone, and that's the thawing front moving upwards through our column. And then over time, you can quite clearly see that this thawing front moves vertically upwards until here at time 15. And that's also right there that you can see that there wasn't any, that all the temperatures were above 0. So all the ice was removed from the column, and you can also see that back in the inversion, it's completely blue, so really low resistivity. So the entire column was free of ice. Yeah, we needed at the bottom to create a 1D system, so a heat pulse moving upwards. Yeah, yeah. So if we would then move back
at the top, I mean, because if you heat, normally you would, in the nature, it would be heated from the top, right?
Yeah, correct.
And the thing is, you generate water, and that water
percolates down,
and then freezes again deeper, and you get an ice wedge that is built up.
Yeah.
Which you don't get in your experiment when you heat from the bottom.
No, that's correct. No, because we really want to look at the temperature, the conductive temperature propagation only, and not the resulting refreezing that you get afterwards. Yeah. Because it was a fully saturated column as well. It wasn't a partially saturated soil. Yeah. But it's fair point. So if we go back to our theoretical temperature resistivity relation there on the left, where you can see this quite clear jump in bulk resistivity as you start freezing, what we did was we extracted the resistivity values for the exact temperatures, and then here on the right you can actually see quite clearly the same jump in resistivity that you get from our from theory actually. But what you could also see quite clearly is that there's actually a hysteresis pattern. So as you start freezing, your resistivity value goes up a little bit slowly, and then when you start thawing it, the resistivity value follows a slightly different pattern. And that actually has to do with the difference in liquid pore water fraction between the freezing and the thawing process. So that was on the work I did so far on soil modeling. And then for the FARMWISE project, so that's the EU project that Martina already introduced shortly. So it's a large EU project, and the research goals are to improve the decision making, so using an AI-based framework and a visual decision support system. So that's a visual decision support system mainly for farmers, where farmers can use that platform to see what kind of decisions they can make regarding the farming, regarding their water use, to better cope with stresses in climate. The second point is enhanced water quality management. So that's the integration of relevant databases and advanced technologies such as smart sensors and DNA-based indicators. So a large part of the project is also on the integration of actually a large number of national databases into a large EU database, so that all the researchers can access all the national data regarding water quantity and quality from one single portal. So that's actually quite a nice outcome from the FARMWISE project also, I think, for the soil modeling consortium, because there you have a really nice overview of all the data that is available from all the partner countries. And a large part of the project also includes these advanced technologies such as smart bio-based sensors. So there are quite a large number of project partners that are working on different sensors or smart techniques that farmers can use to get more data from their field or improve their yield, one way or the other. Future scenario analysis. So the project focuses on modeling different climate and land use change scenarios, evaluating their potential impact on water quality indicators. And that is actually the part that we as the work are mainly involved in. So the modeling aspect. And then also the fourth research goal is to improve agricultural productivity. So again, with a decision support system, we'll provide farmers with important short and long-term management options. And those are mainly driven by the future scenario analysis and also by water quality modeling work that's being done. So here's just a short list of all the partners. So Lund University has the lead on the project. Wageningen we're involved, and it's quite a large list of consortium members, but also quite a lot of them are partners that either have case study sites or that develop smart sensors, for example, that are tested throughout the project. So just a few more slides on what we here at Wageningen are focusing on within the FARMWISE project, and that is has to do with the innovation that is being tested, which is a composite controlled drainage with sub-irrigation. So a lot of fields here in the Netherlands, they contain conventional drainage. So you can see there on the top right, to maintain a specific water level within the fields when it is too wet. But when you collect all the water in your tile drainage into a collector pipe, you can actually control the water level in your field. But what you can also do, and that's being tested in the FARMWISE project, is use the tile drainage to also inject water into the field and thereby create a artificial recharge. And one of the questions here is, what's the effectivity of such a system in terms of water quantity, but also in terms of water quality? So how does phosphate and nitrate within the field respond when you start injecting water into the ground at a specific depth, and how much of that water is actually go to the root zone, and how much water is actually flown directly to the groundwater. So there we have different scenarios that we will evaluate, different future climate scenarios. And one of the objectives is also to see how we can integrate artificial intelligence to simulate part of this process. So as part of my work, we're using hydrogeosphere. Already mentioned it briefly during lunch to some of you. And a hydrogeosphere is a fully coupled 3D model using surface and subsurface flow, with including an saturated zone. And here on the right, you can actually see the field that here in the Netherlands that contains this composite controlled with irrigation system. And we're using hydrogeosphere to simulate the water quantity, so the heads within the field. And then the next step is also to add the water quality to the hydrogeosphere model, and then mainly look at nitrogen and phosphorus, because we're also collecting water samples and measure the nitrogen and phosphorus levels. But this is just a quick simulation on how the model runs. So this is precipitation is being added to the top of the water, and you can see in red in the channels that you have some drainage there. And then the color is the groundwater head. So you can see the groundwater head responds to precipitation as it bulges upwards, and that's then being drained to the ditches. And here in the middle of the field, there is this composite controlled drainage system. I haven't included the irrigation yet, but this is how you can actually simulate groundwater pollution over time as a function of, well, precipitation, evapotranspiration. That's all in the model. I think, yeah, that was it from my side. Thank you. Yeah, questions?